Hello everyone, welcome back to the channel. And in today's tutorial, we'll explore how cutting-edge transformer architectures can revolutionize financial forecasting. Transformers overcome the limitations of traditional RNNs by leveraging self-attention to capture long-term dependencies in time series data. So the tutorial is divided into three parts. So part 1 covers the fundamental theory behind the self-attention, embedding layers, and multi-head transformer blocks as applied to stock price prediction. In part 2, we build a complete Python script using Keras to pre-process stock data, define the transformer model, and train it to forecast future prices. And part 3 focuses on testing the trained model, analyzing training logs, and interpreting the results to understand model performance and potential improvements. So you can find the code repository linked below, which includes the thesis explanation, a Jupyter Notebook, and a ready-to-use script. So by the end, you will have both a solid theoretical foundation and a working code base to adapt for your own time series project. Let's get started and unlock the new possibilities in time series forecasting. Let me start by explaining why we are using transformers for time series forecasting. Traditionally, when we want to predict future values in a time series like stock prices, temperature readings, or sales figures, we have two main approaches. Okay, first, we could use a statistical method like ARIMA models or exponential smoothing, which actually work well for simple patterns, but struggle with complex nonlinear relationship. Second, we could use recurrent neural networks like LSTM or GRUs, which actually processes sequences step by step, building up context as they move through time. But here's some fundamental limitation. These RNNs process information sequentially, meaning they can only look at past information when processing the current time step. And they often struggle with very long-term dependencies because of the vanishing gradient problem. Transformers completely revolutionize this approach. Instead of processing the sequence step by step, a transformer can look at all the time steps simultaneously through what we call self-attention. Think of it like having a team of analysts where each analyst can instantly consult with every other analyst about any time period. Rather than having to pass information through a chain, this parallel processing not only makes training much faster, but it also allows the model to capture relationships between time steps that they are very far apart. Something that's crucial for many real-world forecasting tasks. Here's a powerful analogy that might help you understand this better. Think about how GPT models work for text generation. When GPT predicts the next word in a sentence, it doesn't just look at the immediately preceding word. It considers the entire context of the sentence, paragraph, or even the whole document. It can understand that a word mentioned at the beginning of a paragraph might be crucial for predicting what comes at the end. Similarly, our time series transformers doesn't just look at the yesterday's stock price to predict tomorrow's. It can simultaneously consider patterns from last week, last month, and even seasonal trends from a year ago, just as GPT learns that the capital of France should be followed by Paris by understanding the relationship between all the words in the sentence. Our time series, the same. The model learns that certain price patterns from weeks ago might predict future movements by understanding relationships across all time steps. So, the core innovation here is the self-attention mechanism, which we'll implement from scratch. Before we dive into the code, let me explain the mathematical foundation, the architecture of the model. The self-attention works by creating three different representations of our input data: queries, keys, and values. So for each time step, the query represents what information I'm looking for, the keys represent what information is available at each time step, and the values represent what information should I extract. So the attention mechanism computes how much each time step should attend to every other time step by calculating similarity scores between queries and keys, then uses these scores to create the weight combination of the values. So this is exactly the same mechanism that allows GPT to understand which words in a sentence are most relevant for predicting the next word, except we are applying it to time steps instead of words. So Let's start explaining the model architecture. So you begin with your complete time series, for instance. Here we have, just for example, 60 monthly trade values. First, pick a window size that is a scikit-learn. We're going to see on the code this variable is the scikit-learn. First, that might be 6, 12, or 100 time steps, depend on you. Actually depend on how much history you want the model to see at once. Once scikit-learn is set, you slide a fixed length window across the data. So months 1 scikit-learn, then months 2 scikit-learn plus 1, and so on, until the very last possible window. Each overlap produces one input sequence of exactly scikit-learn points. So next, decide how many of those sequences you load in a parallel. This is your batch size, okay? If batch size, for example, is 4, you take 4 consecutive windows, months, for example, 1, 6, 2, 7, 3, 8, 4, 9, and stack them into a tensor shaped 4, 6, 1 in this case. The final one dimension actually denotes a single feature per time step. By doing this, you let the GPU process all 4 sequences at once. So it's more efficient, of course, than links each 6 points window individually. You repeat the sliding window process until you have generated all possible subsequences in our example. That's 60 minus 6 plus 1, that is actually 55 windows for this specific example. Each training epoch will cycle through these windows either in order or shuffle in a way that preserves temporal validation splits and feeding them into batches through the transformer. Why fixed length windows? Actually, transformers require a uniform set length for every input batch. By extracting fixed length windows, you guarantee that each input sensor has a shape that is batch size, seek length, and features. Without fixed length, actually, the attention mechanism can form consistent query key value matrices. About the batch size, actually, a larger batch size speeds up training by parallelizing more windows, but it also requires more memory. So when creating batches, avoid mixing windows that comes from far apart dates. Why not using the recurrent neural network? That is a classical approach. Actually, RNN process one time step at a time. Even you feed a sec length, for example, 6, it sequentially updates a hidden state, which can struggle to capture direct interaction between non-adjacent steps, for example, month 1 versus month 6. Transformers, with their self-attention, look at all scikit-learn time steps in parallel. For example, you can use 100 time step. They compute an attention matrix of size square, that is sec-length per sec-length, letting the model wake every pair of position at once. After we actually batch the windows of that shape, that is batch size, sec-length, and 1, the next step is to project each scalar into a high-dimensional embedding space. Okay? What we are going to do here, we create embedding vectors. That in our case we choose 128 elements, and that gives you a tensor of shape that is actually batch size, sec-length, and embed dim. This way the model can compute queries, key, and values. In other words, fixed length batched windows are the raw input that enable the embed Q key V attention pipeline. After extracting and batching our fixed length windows, the next step is to give each time step richer representation power that we just explained now. We start with a dense layer of size embed dim, okay, that takes our original scalar, actually this is the stock price, as an input, so one value per time step, and maps it into a higher dimensional space. Concretely, if our input batch is shaped batch size sec-length 1, it will become batch size sec-length embed. So we don't apply any non-linear activation here. This is just a linear, okay, projection that simply learns a weight matrix. Okay, as you can see here, the output is going to be weight, input, and bias. So the goal is to let the network discover an embedding space where temporal patterns become easier to detect. When we have that batch size, sec-length, and embed dim tensor, we create 3 identical looking dense layers, okay, each also outputting embedding feature per time step with a linear activation function. One dance is called QDance, and is this one. Another one is called KDance, and we also have ViewDance. Running our embed input through each produces 3 new tensors. Okay, so the query is Q. Here we go. That is the same batch size, scikit-learn, and embed dim. The keys and the values with the same shape. The reason they share the both shape and activation is that all 3 are conceptually the same projection machinery, just used differently downstream. Okay, think of Q as what I'm looking for, and key what each position offers, and V as what I will actually pass along if the match is strong. So next we decide a number of heads, attention heads, that is going to be an hyperparameter. For example, if embed dim is 128 and the heads number is 8, then the final projection dim is going to be embed dim divided per num heads, so it's going to be 16. So it's just a fraction of the embed dim. We literally split the 128-dimensional Q key V vectors at each time step into 8 subvectors of length 16. In code, this means reshaping from batch size, scikit-learn, and embed dim. We are going to add the num heads, so it's going to be like n heads, so it's going to be batch size, scikit-learn, num heads, and projection dim. It's going to be this tensor n times like num heads in this case. And we also make, we will see later on the code, we apply a transposition of the matrix. So the final shape is going to be batch size, num heads, scikit-learn, and projection dim. Splitting allows each head to attend to different subspaces of the embedding, might focus on short-term fluctuation, another on seasonal trends, and for example, another volatility patterns, and so on. So in total, all, in our case, we decide 8 heads, still cover all 128 dimensions, but in parallel attention computation. Why actually we embed dim instead of direct scalar attention? So transformers rely on comparing high-dimensional query and characters. A single scalar like 23 or 26 doesn't carry enough representation richness. So in effect, each of those 128 dimensions can learn to highlight different temporal features. Is this point near a local maximum, for example? Is this part of low volatility region? So we use 3 separate dense layers, Q, key, and V, because they serve different roles in self-attention. Let's repeat again. So the query layer learns what to look for, okay? That means each query dimension might learn to ask, is there a similar pattern anywhere else in these 6 months? Key layer learns how to describe each time step. The keys becomes reference points. Each time step is encoded so queries can compute a similarity score. And the value layer is actually decide what information to pass forward if a query key pair is a good match. So even though all 3 are linear, using separate weights lets the network optimize its projection for its specific role. So why splitting into multiple heads? So first of all, multiple perspectives. Each head has only projection dim feature to work with, say, 16 out of 128. Therefore, head 1 might learn to focus on very short-term momentum. Head 2 might encode the mid-range season cycles, for example. Head 3 might detect sudden spikes, and at the end we recombine, we will see later, we recombine all the heads so that the model collectively has seen patterns at multiple resolutions. Another reason is the reduced computational cost per head, because each head only has a projection dim dimensions. The dot products, in practice, having smaller matrix multiplication often fits GPU memory better and can be more efficient than one gigantic scikit-learn multiplied per scikit-learn of size embed dim. Another reason is also the gradient diversity, so each head's gradients flow through separate weight matrices. This encourages the model to learn different subspace transformation for Q, key, V, rather than collapsing onto a single attention pattern. So by following these steps, actually, we transform each tensor batch into 3 headwise tensor of shape, batch size, num heads, scikit-learn, and projection dim. So they are now ready for the self-attention.products and softmax operation, which allow each time step to look at every other time step in each of the NumHeads learner subspaces. So the magic of multi-head attention is that it simultaneously learns multiple ways of comparing time steps, capturing short-term, mid-term, and long-term dependencies all at once, before recombining them into a unified embedding representation. So after this, we applied dropout, a regularization technique that randomly drops, sets to 0 actually, a fraction of layer activations during each training steps. By doing so, the model is forced to avoid relying too heavily on any single neuron, which helps prevent overfitting and encourages redundant representations. So in our code, we apply dropout right after the Q key V, just here, after the dense projection, so that during training, each attention head learn to be robust even if some features are temporarily missing. As you can see here, we're going to enter the transformer block. We'll use a multiple transformer block, but we are keeping the Q key dense layer separate here. We're going to take it later. As you can see here in the flow, we're going to take it later for the attention output computation, because now we're going to actually discover the transformer block. So first question, why stack multiple transformer blocks? Imagine you are trying to understand a complex time series, okay, say stock prices over several years. If you only look at short segments in isolation, you might catch a sudden spike but miss the broader trend. By chaining several identical blocks, one after the other, as you can see here, 2, 3, all they share the same exactly structure. It's just one output is going to be the next input. Actually, by chaining several identical blocks, you give the model multiple passes over the data. The first block might pick up on ultra-short ripples. The next block can refine that by noticing weekly or monthly cycles, and deeper blocks can start integrating truly long-term patterns like seasonal effects or gradual growth. How we compute attention score for every single head? Within each block, the very first step is how similar each time step to every other time step. It's time to compute the attention score, actually. We use the query k.product. So now actually is the crucial mathematical operation that defines self-attention. For a single head, we have our query matrix Q and the key matrix key. Actually, we transpose the key matrix. As you can see, the first two dimension is scikit-learn projection dim, and we transpose. We compute how much each time step should attend to every other time step. We perform a matrix multiplication between the queries and the transpose key. So it's going to be Q multiply transpose key. We repeat the computation for all. After that, we need to scale the row score. Those actually row.product scores can become quite larger whenever our subvectors are long, for example. If the numbers showed up too high, actually the next step, the softmax, will drive most of the probability onto a tiny handful of positions, making learning unstable. So to avoid this, we simply divide every row similarity by the square of the subvector length, the projection dim. So in effect, we dump down the magnitude so that the subsequent softmax will be even more evenly and produce smoother gradients. After this step, we are going to the softmax. What we practically do is we convert the similarity score, the scale score, into an actual attention probabilities. So from the previous step, we get a tensor that we saw is batch size, numHead, sec-length, and sec-length. It's a square on the sec-length. And each entry score is the similarity dot product and scaled between a single input value E in batch B head and an input value J in the same batch head. So in the code, we are going to apply this function, this method softmax, with the axis -1. We apply softmax along the last dimension of that sensor in not BHI, but the last dimension. And for each quadruple, the sum of the outputs over the dot equals to 1. Applying the softmax, we transform this dimension in probabilities. Concretely, if you fix batch B, head H, and query position E, the axis -1 means you normalize over all values of J. Here is the formula. And we get an attention weights matrix like this, okay, where on each orthogonal lines, the sum is 1. As you can see here, the red line, this gives you for each input value E a vector of attention weights with respect to every input value J. So those weights sum to 1 across J and indicate how much input value actual tend or weight for input value the stock price. In a self-attention matrix, each token pays attention to every other token. For example, we call it token, but actually token is for the GPT. In this case, is the input value. Is a mistake, actually. For example, we have A, B, C, the same on the vertical line. So we can have attention C comparing to D, but also attention C comparing to C, to itself. So the self-weight, the diagonal one of the attention score matrix after softmax, tells you how much of my own value do I keep when recomputing token, when recomputing the input values is context-aware vector. Okay? This attention weight matrix is computed for each head, of course. And after this, we are ready for the attention output computation. What happened here? Actually, we turn attention weights into context vectors. Okay. Once we have those attention weights, the next step is to use them to mix together the corresponding value vectors. So we get back the value dense vectors, dense tensor that we created at the beginning. We get back here and we multiply. We also use a dot product with the attention weight. So we are going to compute the attention output. The result is a new tensor where its position output actually is a context vector that integrates information from every input value in the sequence with coefficient given of how much attention weight was assigned to each token. In short, it transforms the per position attention distribution into context-aware embeddings by mixing the original value representation according to those attention score. Here you can see the explanation of what we just say. We are going to apply the dot products for each head, of course, and this is the last step of this attention output. We are going to merge all the heads. So we have n heads, and we are going to transpose and reshape. What we do is just merging all heads back into one representation and get back the original embed. You remember here we split here. We are going to merge back again in this spot at this point. So now that each of our heads has produced its own context vector, we already see the shape, batch size, num heads, scikit-learn, and projection D. We need to combine them into a single, that you can see here, of length embed dim, that is num heads multiplied per projection dim. Okay. This merge sensor now has a shape with the original embed dim, as you can see here, and contains the fused information from all heads ready for the next stage of processing. After this, we apply another dropout. After the dropout, we apply the residual connection and a layer normalization here. What we are doing here, actually, the residual connection, as you can see from the drawings, is element-wise sum between attention output and the original input. Now that we have our attention embeddings, we add a residual or also skip connection by summing all this vector. What is the purpose? Actually helps preserve the original information in case the attention sublayer didn't learn anything useful for that feature. Immediately after adding, we apply this layer normalization, which rescaled that sum vector so its coordinates have zero mean and unit variance plus a small epsilon for numerical stability. So the result has exactly batch size, scikit-learn, and embed dim shape. So as you can see here, we just create a small neural networks with value activation. And actually for each element in the sequence, we are going to apply these two dense layers where we expand the original embed dim to we call the code, the variable is ffdim. It's going to be big. We decide, is an hyperparameter, we decide how big it is. But actually, we are going later to get back the same embed dimension, okay? Why we do this? Let's think how we can explain. Now, After the attention mechanism has allowed each time step to gather information from all other time steps, we need a way for each position to actually process and transform that gathered information. So think of it in this way. Attention is like having a conversation where each person, time step, listens to everyone else and takes notes. Okay? But just listening is enough. Each person needs to think about what they heard and form their own conclusions. The feed-forward network is that thinking step. After this, we are going to apply another dropout, another layer normalization. So we are going to repeat for n times. After this, we get the output from all the transformer blocks. So we get tensor with the same shape, embedding, batch size, scikit-learn, and is not divided in n heads like before. So the shape get back to 3. Our ultimate goal is to predict a single number. So in other words, we need one final vector per example that somehow collects all those time steps embedding into a single unified representation. So flattening is the simplest way to do this. Instead of treating the sequences as a grid of shape, we collapse it into a single row of length. We literally concatenate all the embedding in the sequence length in this way. Conceptually, what happens is this. So imagine you have 6 time steps, each represented by 128 dimensional vector. Flattening just means you take the first 128 numbers and then immediately append the next 120 like this. And we get just a long vector. Conceptually, it preserves temporal order. By concatenating in sequence order, the model still knows these first 128 entries came from mount 1, the next 128 from mount 2, and so on. So there is no shuffling. Every time step remains in its original slot along that long vector. And it retains all information, and you also have to consider that enables a denser regression head. After this, we apply another dropout. So even though the transformers blocks already had multiple dropouts, the flattened vector is extremely high dimensional. For example, 6 months multiplied for 128 teams, okay? Applying a final dropout, say for example with rate 0.1, randomly zeros out of 10% in this case, of those 768 features during training. This forces the regression head to avoid over-relying on any single coordinate and encourages robustness. In practice, it means that if some particular time step dimension pair was giving a shortcut, the model has to learn backup signals elsewhere. And in the end, we apply a dense layer to dimension 1, a linear activation, so that single number per batch element is our predicted next stock price. Okay, so now let's begin our implementation. First, we need to set up our environment properly. As you can see here, I'm importing all the necessary libraries like TensorFlow, Keras for our neural network implementation, Pandas. I'm also configuring GPU usage with memory growth enabled. This is crucial because by default, TensorFlow allocates all available GPU memory at startup, which can cause sometimes issues if you are running multiple processes or if you have limited memory. Let's discover this important class. We are going to implement here the heart of our transformer architecture. As we saw before, in the conceptual workflow, we are going to see by code all the previous steps. So this is the heart of our transformer architecture, the multi-head self-attention. This is where actually the magic happens. The multi-head attention gives us all the functionality we need for our gradient computation and parameter management. In the initialization method, we are setting up several key parameters. The embedding parameter, as we saw before, it defines the dimensionality of our input embeddings. The numHead parameters determines how many parallel attention mechanisms we run simultaneously. And instead of having one massive attention mechanism, as we saw before, we split our embedding dimension into multiple smaller heads, each focusing on different aspects of the relationships in our data. So the projection theme here, as you can see, is critical. We are dividing the embedding dimension by the number of heads because each head will work with a subset of the feature. For example, if we have an embedding dimension of 128, and 8 heads. Each head will work with 16 dimensions. This parallel processing is what makes multi-head attention so powerful. Okay, so we can capture different types of relationships simultaneously. So now we are creating 3 dense layers here for query key and value. These are fully connected layers, and they will learn how to transform our input embedding into the query key and value representation. And so let me talk about, let me walk you through the core attention computation here, which is implemented in this attention method. This is where we actually compute the attention scores and apply them to create our output representation. The first step is computing similarity. It's computing similarity scores between queries and keys using matrix multiplication. When we do matmul, this one, with transpose B true, we are computing product between each query vector and each key vector, okay? This gives us a score matrix where each element represents how similar a particular query is to a particular key. So the mathematical operation, as we saw before, is crucial. For sequences of length n, we get an n by n attention matrix where each row represents how much one time step should attend to all other time steps. But row dot products become very large, especially in high dimensional spaces, which can cause the Softmax function to saturate very sharp and produce very sharp probability distribution. So this is why we apply the scaling. After scaling, we apply the Softmax function to convert our similarity score into attention weights. The Softmax ensures that for each query, the attention weights across all the keys sum exactly to 1. So finally, we compute the output by taking a weighted sum of all the value vectors, where the weights come from our attention matrix. Now let's look at the split heads mechanism here, which is essential for implementing multi-head attention efficiently. This function takes our full embedding dimension and splits it into multiple heads. Okay? The reshape operation transforms our tensor from shape, batch size, sequence length, and embed dim to batch size, sequence length, num heads, and projection dim. Then we transpose to get batch size, num heads, sequence length, and projection. Each head now operates on a subset of the original embed dimensions, and they can all be computed simultaneously. The call method brings everything together, orchestrating the entire multi-head attention computation, as you can see here. First, we project our inputs into query, key, and value using our learned heads layers. Then we split each of these into multiple heads using the split heads function here, this part. The transport operation reverse the head splitting, and their shape combines all the heads back into a single tensor here with the original embedding dimension. Finally, we apply one more linear transformation through the combined heads dense layer, which allows the model to learn how to optimally combine information from all attention head. So let's move on to the transformer block, which combines our multi-head attention with other essential components. So a transformer block, as we saw before, consists of 2 main sublayers: the multi-head self-attention mechanism we just implemented, and a position-wide feed-forward network. The feed-forward network is a simple 2-layer MLP that's applied independently to each position in the sequence. This that the first layer actually expands to FFDIM, as you can see here in this part. Typically 4 times the embedding dimension with the ReLU activation that the second layer projects back to the original embedding dimension. This expansion and contraction allows the model, if you remember the workflow, to learn complex nonlinear transformation of the attendant features. After that, we have layer normalization, and the forward pass to our transformer block implements the classic transformer architecture with pre-layer normalization. Notice the residual connection. We are adding the input. Here we are adding the input to each sub-layer output before applying layer normalization. The connection are absolutely critically, as we saw before, for training deep network, because they provide a direct gradient path from the output back to the input. And then we apply also the dropout, and here we go. another layer normalization at the end. And we have the transformer encoder. This actually stacks multiple transformer blocks to create a deep network. The power of stacking multiple transformer blocks is that each layer can build upon the representation learned by the previous layer. So the first layer might learn to identify basic patterns like local trends, seasonal patterns, as we discussed before. The second layer can then use this pattern to identify more complex relationships. So before we can train our model, in this case, we just create a synthetic data set. In the real use case, you are going to put inside your real stock price data, your real-time series. The create dataset function implements the sliding window approach that's standard for time series forecasting here. This function actually takes our univariate time series and create overlapping sequences of length time step as inputs with the next value as the target. For example, if we have data 1, 2, 3, 4, 5, 6 and time step 3, we create 1, 2, 3, 2, 3, 4, 3, 4, 5. We target 5. We target 4, 5, and 6 respectively. This sliding window approach gives us many training examples from a single time series, and it mimics the real-world forecasting scenario where we use a fixed window or historical data to predict the next value. Okay, now let's build our complete model architecture. In this function, build model, we create the entire forecasting pipeline. The architecture starts with an input layer, okay, that expects sequences of a shape, time step, and 1. Each time step has one feature, which is our stock price. The first dense layer is crucial. It projects each scalar price value into a high-dimensional embedding space. This embedding layer serves multiple purposes. It gives the model more parameters. It creates a richer representation space for the attention mechanism. After the transformer encoder processes our sequence and create a rich contextual representation here for each time step, we need to combine all this temporal information into a single prediction. So the flattened layer concatenates all the time steps representation and we saw on the workflow into one long vector. These preserve all the temporal information, but in a format that a standard dense layer can process. We apply dropout one more time for regularization, then use a final dense layer with a single output to make our price prediction. So let me walk you through the complete training pipeline. We go into the main function. This synthetic data combines a linear trend, okay, a linear trend with Gaussian noise, which create a realistic looking price movements with both directional bias and random fluctuation. Using synthetic data actually allows us to understand exactly what patterns exist in our data and evaluate how well our model captures them. We have the data normalization here that is absolutely critical for neural network training. We use a min-max scaler, especially in neural network, especially those using activation functions like ReLU, work much better when inputs are scaled to a consistent range. The min-max scaler transforms our data so all values fall between 0 and 1, which ensure that gradients remain stable during training and that all features contribute equally to the learning process. So after creating our sequence, we build and compile our model. We choose these hyperparameters here, embedding, numheads, ffdim, num layers, and dropout rate. We integrate the tensor board, so it provides powerful monitoring capabilities during training. We also implement Keras that creates beautiful architecture diagrams that help us understand our model structure. Tensor board logging capture detailed information about training process, weight distribution, and computational graph. This is the actual training process and uses a validation split to monitor overfitting. We put 20 epochs that usually is sufficient for this type of problem, and a batch size of 31 provides a good balance between training stability and computational efficiency. For evaluation and visualization, we make prediction and transform them back to the original scale, okay? The visualization allows us to assess model performance and by comparing predicted values to actual values. So good performance means that the prediction should follow the general trend and capture measure movements in the data. So let's test our script. Here, print our model architecture. As you can see here, during training, we see the three primary metrics. The loss, that often is mean squared error in regression task. This is actually the objective the model is optimizing. Measure the average square difference between the predicted value and the true value. In the first, we see 14, that actually meaning on average, the square error is quite large initially, but by the second epoch, the training loss has dropped to really lower, like 0.47, and is decreasing. After we have the mean absolute error, it computes the average of absolute differences between predictions and actuals. It's on the same scale as the original data, so it's easy to interpret. Mi of 2.7 or 0.52.07 means that on average, the model prediction were about 2.07, 2.08 units away from the true price in epoch 1. And it also dropped really fast. We have the root mean squared error here, and it's simply the square error of the MSE, and to translate the squared error back into the original units, and like MAE, but it penalizes larger error more heavily. So as we wrap up, let's take a look at our model performance. And we can see how its prediction compared to the ground truth here with the RMSE. The test loss is really low, and also the other metrics. We can see the prediction plot, but the blue line actually represents the true data, and the orange line shows the transformers predictions. Of course, as you can see here, this is not a real world case. Okay? It's important to emphasize that these results were achieved on synthetic data. In practice, the real stock price have far more complex dynamics, and it's like an unmodeled external factors. As a result, while our model achieves very low MSE, MAE, deploying a transformer on real financial data will require careful feature engineering, regularization, and many other important sophisticated architecture. And you can also activate the tensor board because it saves all the logs, and you just write on the terminal tensor board -log_dir logs, and it's going to launch at the localhost to 6006 port. So you can see all the metrics during the training. It's going to be a lot of interesting informations. And here you can see also the model architecture. You can see some beta histogram and many other metrics, the epoch loss, the learning rate, and so on. I hope this tutorial has given you a solid understanding of how to build, train, and evaluate a transformer for time series forecasting. If you'd like to experiment further, be sure to download the full code repository. The link is in the description. Tweak the hyperparameters or even try it on a real market data. Just keep in mind the additional challenges you will face. Until next time, happy modeling and see you in the next video.